Okay, next we're going to do this section, and this conditional probability and independence will play an important part in some of the data mining videos and some of the marketing modeling videos. Okay, so first of all, we talk about independent and dependent events. So we've talked about events. And now we're going to say what we mean by saying that two events are independent. What does that mean? Okay, so suppose I toss a coin 100 times. And suppose that every time I get heads each time. Is that impossible? No, it's not impossible. It's certainly not likely, but it's also not impossible. So let's call that event A. Okay, so A is that when I toss a coin 100 times, I get heads every time. So event A is not likely, but it's also not impossible. Now let's define an event concerning what happens on the 101st toss, just what happens on the 101st toss. And let's define an event called B. Okay, so I can ask what's the probability of B? And I can also ask what is the probability of B given that we got 100 heads in the first 100 tosses. So first of all, let's define an event called B, which is that on the 101st toss you get a head. So I can ask what's the probability of that, and I think everybody would say, okay, if we're just talking about the 101st toss, the probability of heads, we would say it's a half, just like any other toss. The probability is a half. But we can also ask, so we can ask what's the probability of B. We can also ask what's the probability of B given that we got 100 heads in the first 100 tosses. That is, what's the probability of getting heads on the 101st toss given that we got heads on the first 100 tosses. And I can rephrase that. I can ask what is the probability of B given that A occurred. So what about that? So if you know that you got 100 heads in a row, and we're talking about a fair coin, a 50-50 coin, but you got 100 heads in a row on the first 100 tosses, then what's the probability of B now? So we can also ask that question. Okay. Now that question can be, the way you can express that using a mathematical, or using the notation, is this. Like that. So that doesn't mean divide. It's just a short way of writing this. So I can ask what's the probability of B given A? Okay, it's just a short way of writing that. It's not divide. Okay, that's all. It doesn't mean divide, just means the probability of B given A. So the question is, what would you say about that? What's the probability of B given A? So some people would say, well, since you got 100 heads in the past, it's less likely that you're going to get heads this time because you got so many already. But other people will say, and these people are correct, they would say, well, it doesn't matter that you got 100 heads in a row. We said it was a fair coin, so the probability for the 101st toss to be heads is still 1/2, and the argument for that is that the coin has no memory. The coin doesn't remember what happened in the past. And so we say that what happens on the 101st toss is independent of what happened before that. But anyway, let's first explore this notation, and then we'll come back to this idea of independent. So this notation is called conditional probability. This is a conditional probability question. So the probability of B given A, so A is the condition that we're given, and then we're asked what's the probability of B given that condition. That's called conditional probability. Okay, I'm going to switch to this other book for this. I think it's a little bit better. So from our previous work, we know that the probability of tossing a 1 with a fair die is 1/6. So with a fair die. Suppose, however, that a fair die is tossed and we are told that the number on the top face is odd. What is the probability that the number tossed is a 1? So this is like the question I gave you here. That is, we're given something, some new information, and then asked for the probability of something. So here, the new information is that we're given is we are told that the number on the top face is odd. So we're told that it's odd. Now, what's the probability of getting a 1? So if we just say what's the probability of getting a 1 without that second sentence there, second phrase, we said it was 1/6. But if we're told that the number on the top face, the number is odd, now what's the probability of 1? So you might want to change your answer, because if you think, okay, it's odd, then there's only 3 possibilities now. 1, 3, and 5. So what's the probability that it's 1? Given that there's only these 3 possibilities, you might say it's 1 out of the 3, 1/3. Okay? So whereas before the sample space was 1, 2, 3, 4, 5, 6, now the sample space is sort of reduced to just this, so we call it a reduced sample space. And because of that, we might say that the probability is only 1/3. So in this case, we have an event E that we get a 1, and a different event that it's odd. And the question then was the probability of E given that it's odd, or given that F occurs. So this is E/F equals 1/3. Okay, in probability problems it is usual to abbreviate the phrase E occurs given that F occurs by this. Okay, so that's E given F, so we're asking for the probability of E given F. And the answer we seem to think is that it's 1/3. So how can we sort of come up with a rule for this so that we can calculate that 1/3? Okay, so let's see. Suppose here's the sample space, and here's an event A, and here's an event B. And if we ask for the probability of B, let's suppose that there are a number of different outcomes in here, and there are L of them in B, and they're all equally likely. So then what's the probability of B? If there are n points altogether, I didn't say that, but suppose there are n points altogether, n, and there are L of them in B, and if they're all equally likely, then what's the probability of B? It's L over n. Okay? Now suppose that A, or I guess what we're saying is that A intersect B has m points in it. So there are L altogether here, but some of them are in here. There are m of them in here. So if we ask what's the probability of this, out of all the points, there are n points altogether, and there are m in here. If we ask what's the probability, if all those points are equally likely, it's m divided by n. Okay, so the probability of A intersect B is m divided by n. Now, what we're interested in this question is this. So the probability of A given B. So remember we talked about the reduced sample space. So originally we had this whole sample space. But now we are given the fact that B has occurred. Given B. So given that B has occurred. So the sample space is no longer this whole thing anymore. It's only B. So what's the probability of A? Now, not all of A can occur. right? If this part of A, if there's some point out here, this can't occur. Okay, the only part of A that can occur is where? The part of A that's in B, because we already know that B has happened. So we're limited to B. We have the reduced sample space of B. So what's the probability of A given B now? So it's the size of the number of points in here divided by the number of points in the new sample space, the reduced sample space B. So they write that this is the number of points in A intersect B. We said there are m of them. And the number of points in all of B, we said there are L of them. This is n. This is read n of B. This is read n of A intersect B. N of B and n of A intersect B. So the number of points in A intersect B here divided by the size of B, the sample space. So that's m, the new sample space. So that's m divided by L. Okay? So what's the probability of A given B? It's the size of the intersection divided by the size of B. So what's the probability of A given B? It's the size of the intersection, or the probability of the intersection. The probability of the intersection divided by the probability of the whole thing. So that's the definition of conditional probability. That is the definition of the probability of A given B. That's what we're going to use as the definition. It's the probability of A intersect B, which we've already talked about. We saw that in a video, just recent video, divided by the probability of B. Okay, so let's try an example here. If two fair dice are tossed, so two balanced dice are tossed, what is the probability that the sum is 7? The sum of the two dice is 7. So you might get like a 3 on one die and a 4 on another die. So the sum would be 7 in that case. So what's the probability of getting a 7 if we know that at least one face shows a 4? So at least we know that at least one of them is a 4. Now if I thought about this problem before I studied conditional probability, I would have thought about it like this. I would have said, okay, one of them is a 4, so the other one, in order to be 7, has to be a 3. In order for the sum to be 7, the other one has to be 3. So what's the probability of getting a 3? And I'd say, okay, well, they're all equally likely, 1, 2, 3, 4, 5, 6. So the probability of 3 is 1/6. So the answer must be 1/6, but that's not right. And what do I mean by it's not right? I mean, if I actually did this many, many, many times and counted up the percentage of times that I got a 7 when one of the dice was a 4, I wouldn't get 1/6. That wouldn't work. It wouldn't be true. So my thinking was somehow wrong. So let's see how to do it. Let A and B be the events. A, the sum is 7, and B, at least one face shows a 4. Remember? What's the probability that the sum is 7? So we'll call that event A, given that we know that at least one face shows a 4. So B is at least one face shows a 4. So what we want to compute is the probability of A given B, right? We want the probability that the sum is 7 given B. Okay? So we're going to be able to use this formula. But first, let's make clear what A and B are. So A is that the sum is 7. So if I get a 6 on the first die and a 1 on the second die, then the sum is 7. If I get a 5 on the first die and a 2 on the second, then the sum is 7. Okay, let's just look at the sample space for a minute. So this is the sample space. When we roll two dice, we can get a 1 on the first and a 1 on the second. We get a 1 on the first and a 2 on the second, 1 on the first, 3 on the second, and so up to 1 on the first and 6. And we can get a 2, 1, 2, 2, 2, all the way up to 2, 6, 6. So this is the sample space. We say these are all equally likely if the dice are balanced. And there are how many elements in the sample space? Well, it's 6 by 6, right? So there's 36 elements in the sample space. Now going back to here, A is that we get a 7. So A is a subset of the sample space. It's the subset where you get a sum of 7. So 6, 1 is in there, 5, 2 is in there, 4, 3, 3, 4, 2, 5, and 1, 6. So where's the sum of 7? It's 6, 1, 5, 2, 4, 3, 3, 4, 2, 5, 1, 6. So it's this diagonal set. It's the set containing that diagonal set of points. Okay, so that's A, getting a sum of 7. And B is that you get at least 1, 4. So where's that? At least 1, 4. At least one of the dice is a 4. So all of these have at least one of the die being 4. And all of these have at least one of the die being 4. So there's how many? There's 6 here, and there's 6 more here, but this one I counted twice then, so there's actually only 11. There's 11 of those cases. So B has those 11 elements in it. So now what's A intersect B? Because we're going to need to know A intersect B to do this calculation. So A intersect B is where you get at least 1, 4, and the sum is 7. So that's 4, 3, and 3, 4. Right? The intersection of A and B is that. So what's the probability of that? Well, there's 2 of those out of all 36 possibilities. So it's 2 out of 36. And what's the probability of B? Because we're also going to need to know that. So here's B. And there were 11 of them. So it's 11 out of the 36 possibilities. So 11, 36. So the formula up here will say that the probability of A given B, which was what? That you get, remember I said the answer is going to be 1/6, but I'm wrong. What is the probability that the sum is 7 if we know that at least one face shows a 4? This formula will give us that it's A intersect B, the probability of A intersects B, which is 2 over 36, over the probability of B, which is 11 over 36. So we cancel out the 36, we get 2 11ths. I said it was going to be 1/6, which is 2 12ths. So somehow I guess I was counting that this thing somehow twice in my thinking, because I kind of got 2 out of 12, which is 1/6. The right answer is 2 out of 11. Okay, so that is the idea of conditional probability. The probability of A given B is called the conditional probability of A given B. And this is the formula. And this is like the reduced sample space. And this is just the part of that sample space that we asked for A, but we can only have A as within B. So that's what the top part is. Okay, let's take let's look at this example. Actually, I'll stop this.